Hi friends, let's solve a puzzle and also learn a very useful problem solving technique called numerical simulations. The puzzle is this. Let's say we have a house with 4 rooms, 1, 2, 3 and 4. Now from every room we can go to the remaining 3 rooms. So let's say this is a door, and this is a door between room 3 and 1, and similarly this one is the door between room 4 and 1. Now on day 1, let's say the pet is in room number 3 and it makes one move per day. We wanted to know where the pet is likely to be after 10 moves or 10 days. Okay. Now from each room to every other room, there is a certain probability of making that move. For example, when the pet is in room number 3, the probability of it moving to room number 1 is 0.3. Okay. And similarly, from room 3 to room 2, it's 0.5. Now let's say the pet, it won't stay in the same room for more than a day. So it will make a move to a different room. So the probability is 0. And then moving from room 3 to room 4 is 0.2. Okay. So these are the 4 probabilities we have. So from room 3 to room 1, 2, 3 and 4. Now the important thing is the sum of all these probabilities should be equal to 1. Now if we want, we can say there is certain probability that the pet will remain in the same room, right? So in that case, we can set this to a finite value. For example, let's say we set it to 0.1, and then we would have to modify the other 3 numbers so that the sum is still equal to 1, because that's the total probability, right? All right. We are going to solve this problem using 2 techniques. All right. The NumPy, and similar to how we define the probabilities from room 3, we define the probabilities from room 1. So when the pet is in room 1, what are the probabilities of moving it to room 2, 3 and 4, right? So here we have that probability of moving from room 1 to the remaining 4 rooms. Similarly, from room 2, and this is what we just saw, from room 3 to the remaining 3 rooms, and finally room 4. Now if you see, we set all the diagonal elements, which is the probability of staying within the same room, we set it to 0, but it's not necessary. I mean, as I said, you can define, you can give it a finite probability, but you have to make sure that the sum of each row is equal to 1.0. All right. So let's solve it using this numerical simulation method, which is widely used in science, engineering, and many areas really. All right. So I'm sure you are probably aware of the NumPy random function. So here we have NumPy random choice. So when we define like this, all these 4 numbers, we are denoting these 4 numbers to denote the rooms 1, 2, 3, 4, right, are equally probable. So for example, if I run this function, let's say 100 times, it is likely that 25 times I get 1 as the output, 25 times I get 2, 25 times I get 3, and the remaining 25 times I get number 4. So all 4 are equally probable. Now we want to make use of this function to simulate this process, right? But we know from room 3, the probabilities are not equally distributed to all the remaining 3, including the room itself, right? So if it is 25% probability moving from room 3 to 2, 3 to 1, 3 to 4, and remaining within room 3, then we can make use of this function to simply sample. So the pet is in room 3, where it is likely to move. Just run this, and whatever you get, that would be the answer, right? So from 3, it moved to room number 2. But we know we have we do not have the equal probabilities. So what we do is, to this function, we can also supply the probabilities. Okay. So 0.3, 0.5, 0 and 0.2. Now when we run this function, what happens is, NPy random, it generates a random number between 0 to 1. All numbers are equally probable. Now, if the generated number happens to be between 0 to 3, it will return 1 as the answer. Whereas, if the generated number happens to be between 0.3 to 0.8, it will return 2 as the answer. Now, where is this 0.8 coming from? This is simply 0.3 added to 0.5. Okay. So we have, basically we are dividing the total probability between 0 to 1 into 4 bins. So the first bin is between 0 to 0.3. Second one is 0.3 to 0.8. The third one, which I have not written here, but that's between 0.8 to 0.8. Okay. So that will never happen. And finally, if the generated number happens to be between 0.8 to 1.0, it will return number 4. So that means the cat or pet likely to take or move from room number 3 to room number 4 if the generated number happens to be between 0.8 to 1.0. So we make use of this function to simulate this whole process. All right. So if I run this function, let's say 10 times, 50% of the time, which is 5 times, we are likely to get number 2 as the outcome. As you will see, the 2 is the more common one. The least likely one is number 4 because it has a probability of only 0.2 or 20%. And we will never get room number 3 because its probability is 0. Once the cat is in room 3, it has to move to one of the other rooms. It does not remain in the same room because that's how we defined it. Okay. So those are the basics. Once all those concepts are clear, simulating this problem is super easy. So here we define a function, simulate pet path. It takes this transition matrix, this one, that's the technical name for it. It's called transition probability matrix, but it doesn't matter. So it takes that matrix. It takes the initial starting room. Now on day 1, here we put the pet in room 3, but it could be in any one of the rooms, right? So we can define that. And the number of steps or the number of days, after how many days we want to find out the pet, right? All right. So to begin with, the current room is the start room. And here we define a path. So we are going to see at the end of the 10 steps, what is the path taken by the pet. So for that, we define this variable path. And initially, it's the current room. And here we are simulating it for the chosen number of steps, 10 in this case. We are just calling this function. Okay, we are just calling this function. Here we hard-coded the probability for room number 3, right? The current room. So what we are doing is, here we are just dynamically updating the current room so that the appropriate probabilities are used when sampling or figuring out the next room. Okay. All right. So we find out the next room, we add the next room to the path, and we update the current room. All right. So we run the loop for 10 times. So here we said, we want to simulate it for 10 steps or 10 days, and the starting room is number 3, right? All right. So we do the simulation and we get this path back. So here we have the path, we are just printing the path. So what happened is, on day 1, the pet is in room number 3 and it moved to room number 1 on second day. And then it moved to room number 3, so on and so forth. And finally, after 10 days, the pet is in room number 2. Okay. So does it mean, is it always going to be in room number 2 after 10 steps? The answer is no. This is only one of the likely scenario or one of the possible scenarios, right? Because at every step, we used probability to find out the next room. Now, if we run this again, we might get a different answer. For example, I run it again. So this time, again, we are starting the pet from room number 3, but this time it ended up in room number 3. So does it mean we cannot answer where the pet is likely to be because it seems completely dynamic? We don't know. Every time we run, it seems like it's going to be in a different room. What we can do is we can repeat this experiment many number of times. For example, let's say we have 1,000 houses. We put 1,000 pets in room number 3 and we observe where the pet ended up after 10 steps. And from those 1,000 experiments, we take the final room and we compute the probabilities for it, so that we answer this question in terms of probabilities, because it's not going to be absolute. Okay, because we can never say that it will be in room number 1 or room number 2. What we can say is, hey, there is 70% chance that it will be in room number 1 after 10 steps. There is 30% chance it will be in room number 2. There is no chance it will be in room number 4. So we can answer this puzzle in terms of probabilities only. Okay, that's what we are going to do. All right. So here what we are doing is we are repeating the same experiment 20 times. Okay. So here we have a new variable called final rooms. So what we want to do is we want to repeat this experiment and we want to collect the final room. All right. So do the simulation for n number of times, calling the same function, and we are collecting the final room from the last element. Okay. All right. So here we have the results from 20 simulations. So every time the cat start from room number 3, it took some path and finally ended up in room number 4 in the first 3 experiment, but in room number 3 in the 4th experiment, room number 1 in the 5th experiment, so on and so forth. And if we collect the final rooms, this is how they are, right? So these final room we have collected here. But simulations, we repeat hundreds of thousands of times, so that the more times we repeat, our approximate solution will converge to the exact solution if we can solve this problem in an exact manner. We will see that also. So what we do is, here we are running it for 1,000 times, exactly the same thing. But once we collected these final rooms, all we are doing is, hey, out of these 1,000 experiments, how many times the pet ended up in room number 4? Do the compute or count how many times it ended up in room number 3, 1 and 2. And simply divide those numbers with the total number of experiments, so that we will get the probabilities. Okay, so that's exactly what we are doing here. So our final probabilities or answer to this puzzle is that after 10 steps, the probability of the pet to be in room number 1 is 0.21. Okay, for room number 2, 0.3, for room number 3, 0.34, and finally 0.14 for room number 4. So to answer this question, after 10 steps, the pet is more likely to be in room number 3 and least likely to be in room number 4. So there is double the chance that it will be in room number 3 compared to it will be in room number 4. Okay, so the final response is also in terms of these probabilities. Okay, so that's the numerical simulation approach we took. And the second one, exact analytical method. So this problem is actually so simple that we can solve it analytically. So we already saw we have a transition matrix and we have the initial state which is where the cat originally or on day 1, which is this room number 3. So 0, 0, 1, 0. Now, yeah. So here we have a transition probability matrix, but for 3 rooms. Okay, so this pi 1 1 that represent probability of moving from room 1 to 1, from 1 to 2, 1 to 3. Okay, so let's imagine we have only 3 rooms. So here we have a 3 by 3 matrix. Now let's just multiply this matrix by itself, or we are taking the square of this matrix. Okay, when we take the square, we get the result like this. Okay, let's closely examine what this element actually means. So here we have pi 1 1 multiplied by pi 1 2 plus pi 1 2, so on and so forth. Now what this is saying is this is the probability of moving from room 1 to 1 multiplied by probability of moving from room 1 to 2. So what it means is this element represents the probability of moving from room 1 to room 2 in 2 steps. In the first step, it remained within the same room. In the second step, it moved from room 1 to 2. Similarly, this represents the same probability, but this time the cat moved from room 1 to room 2 in step number 1, and in step number 2, it remained within the same room. Here is another possibility that it go from room 1 to 3 and then from 3 to 2. Okay, so all these elements are simply representing the different possible ways of going from room 1 to room 2. Okay, so room 1, room 2. So as you can see, it's always start at 1 and end at 2. So we are looking at the first and the fourth element here, 1 and 2, 1 and 2, 1 and 2. So this term represents, these are all the possible ways of going from room 1 to room 2 in 2 steps. Okay, since we took the square of this matrix. If we take the power of n, this element represents the different ways of moving from room 1 to room 2 in n number of steps. So the intermediate steps can be maybe 1 to 3, 3 to 2, 2 to 1, again 1 to 2, right? So we would have, in the first element, we would have pi 1, and in the last element, we would have pi this 2, the fourth, this element, right? So by multiplying this transition matrix by itself n number of times, each element is simply representing all the ways of moving from a certain origin to a certain destination in n number of steps, n being the power of this matrix. Okay, so what it means is we simply take the power of this matrix with the number of steps, which is 10, and we multiply that with the initial state. That will give us the final state. Okay, so our initial state is this. We simply took our transition probability matrix and then took the power of number of steps, which is 10, and here we have the final state. Now if we are simply printing this final state, which will have 4 numbers, which are the probability in each room after 10 steps. Okay, so here we have 0.2, 0.3, 0.35 and 0.14. This is the exact solution. So if you go back, this is our simulated solution. Sorry. Yeah, this is our simulated solution. Now, here we have run this experiment 1000 times. The more number of times we run this experiment, these 4 values get closer and closer to these 4 values. Okay, so in simulation we find this approximate solution, but the more times we repeat this simulation, the solution will approach to the exact solution. Okay, so that's our final answer. I hope you like this puzzle. Now, if you are into probability and numerical simulations and solving a variety of problems using similar techniques, I have a mini course. I provide the link in the description. So it starts with very basics of probability and how to compute the probabilities using simulations, etc. Okay, So please check out that course. That's all for this video. Thank you very much.